Okay, we're finally ready to talk about our first real application of probability theory, and that's going to be to something called hypothesis testing or detection theory or decision theory. So let's talk about binary hypothesis testing. Okay, so the way to think about this is that we're going to use probability as a foundation for principled decision making. Okay, so we're going to observe some measurements. So we're going to make some partial, noisy observations, and then we're going to try to make a decision based on those measurements. Okay, and this is known in the literature as detection theory or hypothesis testing, right? And there are, of course, many ad hoc ways in which you could make decisions based on observations, but we're going to try to do this in a rigorous way. So we're going to see how probability is a really great fit for this scenario. Okay, and so the key idea underlying all of this is that we're trying to decide which of two mutually exclusive events occurred during using one of our observations. Okay, so we use an observation to try to decide what actually occurred. All right, so let's just talk about some examples. And by the way, you could have more than two events, and we'll see that in a subsequent video. So right now we're going to focus on the binary case of just two events, because that's where you get most of the intuition and the analysis is more or less the same. So it's just useful to start with two. All right, so as an example, let's talk about digital communication. So in digital communication, let's say I'm trying to transmit a bit down a wire. I observe a voltage, so I receive a voltage, and I try to determine if a 0 was transmitted as my bit or a 1. All right, another example, let's talk about cancer detection. So let's say I take a CT scan. So based on a CT scan, is a tumor present or absent? Okay, so this is kind of getting at the key thing. In both of these two examples above, there's a true underlying thing that I want to know, whether it's 0 or 1, or whether the tumor is there or not. But I don't get to see that directly. I only get to see some kind of related measurement. And let's talk about quality control. So let's say I have a factory and I'm measuring my parts after manufacturing them, and I want to know that based on my measurement, is a manufactured part defective or not defective? So should I keep it or throw it out? And we're focusing here only on two events and scalar observations. So I just make one single measurement. I get a single number, and it's going to be relatively straightforward to extend this to more than two events and more than a single number as my measurement, and we'll see that later. So once we have the intuition and the framework from binary hypothesis testing with scalar observations, then it'll be easy to go ahead and generalize it. Okay, so let's see what that framework should look like. So we're going to need to define a few new terms. So there are going to be two hypotheses, okay? So two hypotheses, and we're going to call them H0 and H1. And you could call these whatever you like, but this is a pretty common choice in the literature, so it's good to see it. And these are just going to be events, all right? And they are going to partition the underlying sample space, omega, okay? So here is my partition. So I have this red and blue region. So one is H0 and the other one is H1. I'm just trying to abstractly draw what this looks like for you. Okay, and this is what we might call the state of nature. Okay, you won't see this used too often, but the idea is that this is something you're very interested in knowing, but it's not something you have any control over. Okay, so there just is some phenomenon you're trying to decide, did it happen or not happen? And how that comes about, the probability model governing that is something that's controlled by nature, not by you. All right. Then you're going to make a measurement. So you're going to get a measurement or an observation, and we're going to use those terms interchangeably. And that's just going to be a random variable. Let's call it y. All right. And we're going to say that its values are going to be distributed according to one of two possible distributions. Okay. So in the discrete case, what's going to happen is I'm going to see either P of y given H0 of y if H0 occurred. So I'm going to have a conditional PMF that's only going to come into play if H0 indeed occurred. Otherwise, I'm going to see y drawn from Py given H1 if H1 was the thing that truly occurred. So I don't know which distribution is actually going to be there until I get the realization of the hypothesis. In the continuous case, it's the same thing, except I just replace PMF with PDF. So I have conditional PDF given H0, conditional PDF given H1. Okay. And so this is something that we model. So we get this measurement, and maybe we even design the apparatus to collect the measurement, and so we know how to model it. But in any case, we understand the physics and distributions here in order to make a probabilistic model of how measurements look if H0 occurs and how measurements look if H1 occurs. Okay, so these things in purple are sometimes called likelihoods. Okay, so you'll see that language thrown around, and it'll emerge in some of the things we're talking about. So it's useful to just notice that these conditional PMFs and PDFs are called likelihoods in this context. Okay, so let me draw the two distributions in the continuous case. Okay, so this is just an example of what you might see. All right, so what's happening is if H0 occurs, then I get this blue distribution for Y. If H1 occurs, I get this red distribution for Y. Okay, and here these look basically the same. Maybe they're shifted over by a mean shift. And I'm trying to determine which one has occurred based on observing the value of Y. How am I going to do that? Well, I'm going to design a detector or a decision rule. And this decision rule is just a function. What this function is going to do, it's called U, so it's really called D. So it's a function D. It takes in Y, and it outputs 0 if it thinks that H0 occurred, and it outputs 1 if it thinks that H1 occurred. Okay, now here's the problem. So we get to design this, that's all well and good, but the problem is that the detector doesn't get to look at H0 and H1, it gets to look at Y, and then it has to make this decision about what hypothesis actually occurred based only on Y. And if you look at this picture above, the distributions overlap. So they're not completely separated. So it's possible in this region where red and blue overlap that I'm going to make some mistakes. Okay? So that is the thing that we're trying to avoid. I'm trying to always make the correct decision, but since H0 and H1 could both lead to the same measurement value of Y, it is possible to make mistakes. Okay? And one thing I'll just mention as a technicality, in this class, we will not assume that the detector itself is a random function. So it's just a deterministic function of Y. Sometimes it's useful to allow it to have some of its own randomness just to clean up some smaller issues that can occur, but I don't think it's worth it to introduce that. So we're just going to say that for every given value of Y, you either decide 0 or 1 deterministically. All right. So what it's doing, so to make that concrete, the decision rule is creating a partition of the range of Y, okay? So I have a range of my measurement, whatever that is. Maybe it's real numbers, maybe it's something discrete. But in any case, I'm deciding that part of that is where I'm going to decide 0, and part of it is where I'm going to decide 1. Okay, so this is my partition. My partition is A0, A1. Those two sets together form a partition, and meaning that if a value belongs to A0, it can't belong to A1, and vice versa. And together, they cover the whole range of Y. Okay? So we're going to say an error occurs if what I decide is wrong. So if I decide H0, but actually H0 was the thing that occurred. Okay? Or if I decide H0, but H1 was actually the thing that occurred. Okay? So how do I write this as an event? Well, if I want to write it as an event, error is when Y falls into A1, but H0 is the thing that occurred. So I take the intersection of Y falling into the decision region, A1, with H0. And I take the union of that with Y falling into A0 when H1 actually occurred. Okay, so those are the two ways an error can occur where the hypothesis generates a Y that falls into the wrong decision region. Okay, and a really important measure of performance is the probability of error. Okay, so I have my error event, and I just want to know what's the probability that occurs. And we're going to call that P with sub E. Okay, so this P sub E in purple, we're going to define what that means. It's just the probability that an event occurs. So, I could simplify this thing that I have up there. It's basically an instantiation of the law of total probability. So I split the probability of error across H0 and H1 as my partition, okay? And the nice thing is that once I condition on H0, then I know the only way I can make mistakes is if I accidentally fall into A1, the other decision region. So this first probability of error is when y falls into A1, given that it's H0 times the probability of H0, plus the probability that y falls into A0, given that H1 occurs, right? So once I condition on H0 and H1, I know that the only thing that can go wrong is I fall into the other decision region. And this is one way of writing the probability of error. Okay, so this is a really important metric. In the discrete case, we can further simplify this. So the probability that y falls into A1, given that H0 occurs, is just the sum of the values in A1 times the conditional PMF. Or sorry, I just sum up the values in the conditional PMF where y falls into A1. We're going to see examples of this. Same thing for y falling into A0, given that H1 occurs, I sum up over the values of A0 the conditional PMF of y given H1. In the continuous case, I'm going to do the same exact things, but I'm just going to replace the sums with integrals over the region A1 here, okay, with the conditional PDF given H0, and here I'm going to have an integral over the region A0 given the conditional PDF given H1. Okay, and so this is all kind of abstract. It's going to be easier for us to understand what's going on if we visualize it. Okay, so this is just a quick intro to probability of error, but let's visualize it to see what's going on. Okay, and part of that visualization, I just want to point out that one of the motivations for detection theory in the first place was detecting aircraft using radar. Okay, so this actually informed some of the terminology, and we're going to see that right now. So the idea was that there are two ways of making an error in this case. There's the probability that we're going to call false alarm, okay? And we're going to call that P sub FA. And that's this thing, probability that y falls into A1, given that H0 occurs. So think of H0 as the event that there is no aircraft, okay? Yet A1 is when you decide there is an aircraft. So then if you decide there is an aircraft, when there's no aircraft, that's a false alarm. Similarly, the other side of it is the probability of misdetection. Okay, so P sub MD. This is the probability that y falls into A0. So you decide that there is no aircraft when there in fact is an aircraft, H1. And so you missed it. So you missed detecting that aircraft. All right, so let's draw something. So let's draw in the discrete case what we should expect to see. So here is the conditional PMF for y given H0, and here's the conditional PMF for y given H1 in red. And I'm going to also put in these red values here and these blue values here. And I'm just going to pause and tell you what's going on once I've written this. Okay, so the idea here is that across the whole range of y, I could either be seeing the value y because it came from H0 or because it came from H1, but I have to decide one way or the other. Okay, so let's just decide that all the positive values are going to go into A1 and all the 0 or negative values are going to go into A0. Okay, so that's what we're going to do. So here's A1 positive values, and then negative values and 0 go into A1. So what's the probability of false alarm? I take all of these blue values here that fell into A1 and I add up their probabilities. Okay, so this is the probability that in this case, let's say the aircraft is not there, yet I got a positive value of y and I decided it is there. And so I sum up those probabilities and I get the false alarm probability. Okay, and so for the misdetection case, I go all the way to A0 and I sum up all these values where I don't think an aircraft occurred because I got a 0 or a negative read, and that is my probability of misdetection. So I sum up the red values because those correspond to the conditional PMF given that H1 occurred. Notice, so one thing I want to point out here is that even though in most of the cases I took the lower values into the sum, that didn't have to be the case. All that matters is that I've declared them to be either for A0 or for A1. And then for A0, I take all the red terms, and for A1, I take all the blue terms, okay? And this decision rule may or may not be a good one. Here it'll turn out to be relatively good, and we could, think about the nuances of what happened at 0 a little bit later. But really what matters is just where you declare A0 and A1 occur. Okay, let's do the continuous case as well. In the continuous case, these are just cartoons of what kind of distributions you might get. So I might get this blue distribution, and maybe I get this red distribution. So the blue distribution is when H0 occurs, and the red distribution is when H1 occurs. So I'm drawing my A1 and A0 regions just arbitrarily, okay? So now what's happening is when Y falls into the region A0, I'm declaring that H0 probably occurred, and so there I'm going to get my probability of misdetection, and A1 is where I think something did occur, so if I fall into that from blue, I get false alarm. Okay, so let's see that. So I integrate over A, the conditional PDF given H0, that's my probability of false alarm. It's this area. So I find the blue curve, the conditional PDF for H0, and I integrate it over the region A1. All right, and to get my probability of misdetection, I go over A0, and I integrate, and I get the probability of misdetection. Okay, so, and that's it. So then to get the overall probability of error, what I do is I take these two values, probability of false alarm and probability of misdetection, and I just weight them by the corresponding probabilities of those hypotheses, and I add them up, and that's my probability of error. And if you go back to the formula on the previous page, you'll see that that's exactly what it should be. In this continuous case, the reason I broke up this region, A0, is just to show you that the region does not have to be contiguous. It can be broken up, okay? It could be broken up quite a bit. You can just decide which values of Y go into A0, which ones goes into A1, and you should do that in a way that tries to get the lowest probability of error, okay? But you can break up those regions however you like. All right, so that's going to be our job. Our job is going to be to design a decision rule, right? Not a measurement device. So someone has designed the measurement device, and that we know the probability model for measurements given the hypothesis. Our job is to design the decision rule that looks at the measurement and tries to get the lowest possible probability of error, okay? And I might make mistakes, but I just want to try to keep the probability as small as I can. Okay, and the best case would be that I get the smallest possible probability of error. Okay, so we're going to look at some candidate decision rules. So here's the first one. The maximum likelihood rule, abbreviated ML rule. So we write this as DML of Y. That's going to select the hypothesis with the highest likelihood value. Okay, remember the likelihood is just this conditional PMF or PDF that we have. So what I'm going to do is plug in to those conditional PMFs or PDFs, see which one has a higher value for the Y that I plugged in, and I'm going to pick that hypothesis. So in the discrete case, how this looks is that I have this function DML, and it's going to say 1 when the conditional PMF evaluated for H1 is higher than that for H0, and 0 when H0 has a higher conditional PDF. And by the way, note that I am arbitrarily assigning when they're equal to the decision 1, and that's fine. It doesn't matter how you do that. You could also decide, you could send it to 0 if you like. It will not affect the probability of error. We're just doing that here for convenience of notation. Okay, let me show you what this is going to look like again with a cartoon. So let me draw my blue conditional PMF for probability of Y given H0, and my red one for the probability of Y given H1. Okay, so here we are. So this is what A0 and A1 are going to look like. So first of all, let's look at this first position. This is discrete, so I'm just going position by position. So I'm going to decide that blue is higher, and blue came from H0, so I decided that goes into A0 because I'm going to decide 0. Again, I'm going to see for the next one, blue is higher, so that's going to be A0. Then the next one, red is higher, so I'm going to decide that red or H1 is the higher conditional PMF, so I should put it in A1, and that's going to happen for a while. I get A1, A1, and I go back down to A0, and then back up to A1. Okay, so just as whichever one of these is higher, blue or red, then I pick A0 or A1. Same thing in the continuous case, except I just replace the PMFs with PDFs. So I'm going to decide 1 when the conditional PDF of Y given H1 is larger than that of Y given H0 for the specific value of Y. and 0 otherwise. And again, when they're equal, I'm just arbitrarily assigning that to 1. Let's look at a cartoon and see how this is going to play out. Here's my conditional PDF y given h0, and here's my conditional PDF y given h1. So where is blue higher? Blue is higher on this orange part, and then red is higher for a while, and then blue is higher for a while. So this orange region is going to be A0, and the green one is A1. So ties, as I've mentioned, so here I'm talking about the discrete case, we can break them arbitrarily, but we're just mapping them to 1 for our own convenience. Okay, and this is something, if you get deeper into detection theory, you can try to understand what the nuances are about that, but it really doesn't matter at the level we're dealing with it. So you can just assign it to 1 and it's not going to matter. Okay, let's do an example. So in this example, I'm going to have 2 hypotheses. Given that H0 occurs, I'm going to have the conditional probability model that y is binomial with parameters 3 and 1/2. Alternatively, if H1 occurs, then I'm going to say that y is binomial and it's going to have parameters 3 and 1/4, or sorry, 3/4. Okay, so the PMF for a random variable, let's say x, which has binomial np, then remember that that PMF is going to be n choose x times p to the x times 1 minus p to the n minus x for x between 0 and n, and then it's going to be 0 otherwise. Okay, so recalling that, so we just recalled this family of discrete random variables, I can write these PMFs. So for the H0, I'm just plugging in the parameters 3 and 1/2 for n and p, and I get this conditional PMF, and it's going to range from 0 up to 3. Okay, and I'm going to work this out. So I'm going to just try to get all the exact values so we can see exactly how these compare. So I get 3 choose 0 times an eighth for y equals 0, 3 choose 1 times an eighth for y equals 1, 3 choose 2 times an eighth for y equals 2, and 3 choose 3 over 8 for y equals 3. And so this is all going to work out to be an eighth for y equals 0, 3/8 for y equals 1, 3/8 for y equals 2, and 1/8 for y equals 3. Okay, let's do the other conditional PMF for H1. So that's going to be, again, 3 choose y, but now it's going to be 3/4 the y, and then 1/4 to the 3 minus y. It's going to be y from 0, 1, 2, 3, and 0 otherwise. As before, we're going to just work this out. I get 3 choose 0 times 1 to the 6 over 64 when y is 0. 3 choose 1 times 3 over 64 when y is 1. 3 choose 2, 9 over 64 when y is 2. 3 choose 3, 27 over 64 when y is 3. Okay, and so that simplifies down to 1 over 64 for y equals 0, 9 over 64 for y equals 1, 27 over 64 for y equals 2, 27 over 64 for y equals 3. So we're trying to be really explicit about what these values are so I can draw a table for you, and these comparisons are easy. But if you wanted to make the comparisons directly at the formula level for this first formula that I drew, that would be fine as well, and it would work out. So here's my table. I'm just filling it in with an eighth, 3/8, 3/8, an eighth on the first row for the conditional PMF of y given H0, and on the second row, a 64th, 9/64, 27/64, and again, 27/64 for the conditional PMF of y given H1. So the ML rule, we're going to work it out, okay? So it's going to be 1 and 0, and where is this going to occur, okay? So where is the first position? So where are the positions where one is larger than the other? Okay, so we're going to go case by case. For y equals 0, an eighth is larger than a 64th. So I give y equals 0 to A0, and so I decide 0. Okay. The next value, 3/8, is larger than 9 over 64, so I put 1 in the decision for 0. Then I look and I see that 3/8 is actually 24/64, and 27/64 is larger than that. So I pick 2 for the deciding 1. And again, 27 over 64 is larger than an eighth, so I pick 3 for deciding 1. So my decision regions, A0 is where I decide 0. I decide 0 when it's 0 and 1. And A1 is where I decide 1. That's when y is 2 and 3. Okay, so that wraps up this example. At least this first part where I'm trying to learn the ML rule. But what if I now want to know the probability of error? Okay, so we're just carrying this table up. So now I have my decision rule, I have my table, I have my decision regions. I can work out the probability of error for the ML rule. Okay, that's what we're going to do. We're going to call this P of E to the ML. Okay, and here's the formula. So the formula says take the probability of false alarm times the probability of H0 plus the probability of misdetection times the probability of H1. Now, here's the weird thing. We didn't actually specify either of these terms, the hypothesis probabilities, in the problem statement. We should have, right? But I'm just trying to point out to you that without them, I can't proceed any further. It's kind of interesting. I can come up with the ML rule, so I know how to make my decisions using only the measurement model, y given the hypothesis, but I don't know how to calculate what the resulting probability of error should be because I don't know the balance between H0 and H1, how often one occurs or the other occurs. Well, I'm just going to add it to the problem statement in this case, so let's just say that we do know it. So let's say, kind of arbitrarily, that probability of H0 is a fifth, and the probability of H1 is 4/5. Okay? And so now I have the probability of false alarm. I'm just adding up over A1 the probability of y given H0. That's the definition of false alarm. It's where I think it's 1, but it actually came from 0, so I add up the conditional PMF for 0. So I'm going to get for A1, which is going to be 2 and 3, I'm going to get probability of y given H0 of 2 plus probability of y given H0 of 3. Okay, and that's going to be 3/8 and 1/8. Okay, and that's going to be 1/2. Okay, so those are the green entries in the table. Okay, probability of misdetection. I'm going to have the sum over A0, so where I'm deciding 0, but actually there was something there. So probability of y given H1. And so I'm going to get probability of, so I'm just doing it from the table now. So I'm saying that that's going to occur when y is 0, and that's going to give me a 64th. And when y is 1, that's going to give me 9/64. Okay, and so summing that up, I get 5/32. So I can just now combine everything together to get the probability of error overall. I'm going to get 1/2 times a fifth plus 5/32 times 4/5. Okay, and that's going to work out to be 9/40. Great, okay, we have a decision rule. And so the next thing we should naturally ask is, can we do better than this? So was there a better decision rule that would have given me a lower probability of error? And just by virtue of the fact that I'm asking that, the answer is yes. Okay, so it turns out that the maximum a posteriori rule, MAP rule, okay, DMAP, that is actually going to select in a different way. It's going to select the hypothesis that was the most likely given the observation. Okay, so this actually, before we even write down the math, this makes more sense. Before, we were saying, choose the hypothesis that best explains the observation. But I don't care about explaining the observation. I care about what actually happened. So what I should be doing is taking my observation and trying to decide which hypothesis had a higher probability given that that observation occurred. Okay? And we're going to see what that looks like. So first, we're going to just write down the MAP rule in the way that you're going to use it for solving problems. But then I'm going to show you why that corresponds to this intuition. Okay, so in the discrete case, what I'm going to do is I'm going to have the MAP rule. And the MAP rule is going to have decide 1 when the probability of y given H1 times the probability of H1 is greater than the probability of y given H0 times the probability of H0, and 0 in the other case. So the only difference here between the MAP and the ML rules is in the MAP rule, I multiply by the probability of the hypothesis. So I weight by the probability of the hypothesis. Okay, so let's do this in our example. So I'm going to draw a conditional PMF here. So here it is. So here's the conditional PMF for y given h0, and here it is for y given h1 in red. Okay? And so what's actually happening then, if I want to illustrate it, is now I'm going to scale these by their probabilities, okay, by the probability of the hypothesis. Let's say this one is a third for the example. So this gets scaled down by 3. And let's say that, therefore, probability of h1 is 2/3. So I scale this down by 3/2. So then I get these values. Okay, so if you look at the above chart, you'll see that blue was larger for all the negative values, okay? Whereas in the bottom chart, blue is only larger for one value, okay? The other one, blue and red are equal. All right, so then what I'm going to end up doing is deciding that every one of these except for one is going to be green, which corresponds to deciding 1 for A1. And the reason we do that is that ties are going to go to 1 in our way of deciding. Continuous case is the same thing again. So I'm going to have the map decision rule. And what the map decision rule is going to do, it's going to take the PDF weighted by the probability of the hypothesis and see which one is larger. So when H1 is larger, I pick 1. When H0 is larger, I pick 0, and I give ties to 1. Here's a picture. So here are two conditional PDFs, blue and red for 0 and 1. Okay, and again, I'm going to scale these by 1/3 and 2/3. Okay, I'm just plugging in that number so we can draw something. So the blue one's going to go down by a lot, the red one by less. And you can see that before, blue was the larger one up until y equals 0, and then red was larger. But here it's shifted over, so now y is also larger in part of that negative range. So we're going to give that part where blue is larger to A0, okay, and then the rest to A1. Okay, so how does this rule line up with our intuition? Okay, so how did we actually arrive at this rule? I'm just going to do it for the discrete case. So what the intuition said is choose the hypothesis that is the most likely given the observation, which is actually this kind of probability statement. So choose H1 if it is more likely given that y is equal to little y, the thing that you observed. Okay, well, let's use Bayes' rule and write this out. This is the probability of y equals y given h1 times the probability of h1 divided by the probability of y equals y. Same thing on the right, except I replace h1 with h0. Okay, this is just applying Bayes' rule to the left and right-hand sides. Okay, and so the thing to notice here is that on both the left and the right-hand sides, I have in the denominator the probability of y equals little y, and so I can just cross that out. So what I'm left with for my decision is the probability of y given h1, so the conditional PMF of y given h1 times the probability of h1 versus the probability of y conditioned on h0 times the probability of h0. So that's actually how I arrive at that decision rule. I'm using probability of hypothesis given measurement, then Bayes' rule, then crossing out the denominator because it's always going to be the same on both sides, because in both sides I'm comparing the same value of y. Okay, let's go back to our example and see how the map rule applies. Okay, so what I want to know here, I already worked out the ML rule, I worked out its probability of error. So what is the corresponding map rule in this setting? And what is the probability of error and how do they compare? Okay, so in this case, I'm going to have the same table, but now I'm going to multiply by the probability of my hypothesis. So remember, we decided that the probability of H0 is 1/5 and the probability of H1 is 4/5. So I'm going to take this first row from the table above and multiply every entry with 1/5, and the second row and multiply every entry by 4/5. So let's just work that out. So I'm going to get a 40th, then 3/8 times a 5th. That's going to be 3/40ths, then 3/8 times a 5th again, 3/40ths, and then an 1/8 times a 5th. That's going to be 1/40. The second row I get 64ths times 4/5. That's going to be 1/80th. 9 64ths times 4/5. That's going to be 9/80ths. And 27/64 times 4/5. That's going to be 27/80ths. And again, I'm going to get 27/64 times 4/5. That's going to be 27/80ths. Okay, so as before, what I'm going to do is I'm going to just try to decide which one is larger. So the map rule is going to pick the hypothesis which has a larger value in that column. Okay, so let's get started. So in the first column, I'm going to put in blue the larger value. That's going to be 1/40th instead of 1/80th. So y equals 0 is going to go towards hypothesis 0. Okay, in the next column, it's 9/80ths is larger than 3/40ths. So that's going to go to hypothesis 1, and the same thing for the other two entries. So 1, 2, and 3 are going to be deciding 1, and then y equals 0 is going to decide 0. So you see there's a difference in this case between the map and the ML rule in that y equals 1 is now assigned to hypothesis 1. Let's work out the probability of error. So the probability of error is the probability of false alarm times the probability of H0 plus the probability of misdetection times the probability of H1. Okay, so probability of false alarm is now going to be larger, right? Because I have a larger decision region for A1. I'm adding up the conditional PMF of y given H0. So I have probability y given H0 at 1. And then again at 2. I'm circling those in green, the values that I need. And then in 3. So these are going to be the values that I actually need. And so I'm going to get 3/8 plus 3/8 plus 1/8, which is 7/8, which seems kind of high. So I'm making a lot of false alarms when there actually is something coming from H0. But the point is that H0 doesn't happen that often. It only happens 1/5 of the time. Okay, so it's okay to increase this imbalance. Probability of misdetection is only going to be one value. So there's only one value where I'm deciding 0. And so I'm going to take the conditional probability of y given H1, and that's going to be evaluated at 0. Okay, so probability of y given H1 at 0, that's 1/64. So I'm going to get 7/8 probability of false alarm times 1/5 probability of H0 plus 1/64 probability of misdetection times 4/5. That's going to be 8/40. And what I notice is that 8/40 is smaller than 9/40. So map here outperforms ML. So the map rule is better than the ML rule here. Okay, so we found a better way to do this. So it turns out that the map rule is actually optimal. You can do no better than this. All right, so it attains the smallest possible probability of error. All right, that's great. So we found the best possible thing to do. If I know the probabilities of my hypotheses and I know the conditional probabilities that lead to my measurements, I can use the map rule and always make the optimal decision. I might be wrong sometimes, but I can't do any better in terms of probability. Why is it the best? Well, let's expand out the probability of error and try to understand that. So here's one expansion of the probability of error conditioned on y. Okay, so what I do is I try to figure out what is the probability of error given that y takes on a certain value, weight that by the probability of y, and sum up over y. This is just one way of using the law of total probability. Okay? Notice that the probability of error for y equals y is equal to the probability that it's H0 if I'm deciding 1 here. It's the probability of H1 given y if I'm deciding 0. Meaning that I only make mistakes if the hypothesis that occurred is the opposite of the decision that I would make for that particular y. So I'm just going to plug in these values. Okay, so what I'm saying is I have the probability of y is above, and so I'm going to have dy times the probability of H0 given y plus 1 minus dy times the probability of H1 given y equals y. Let's understand why that's the case. So when dy is equal to 1, then I see probability of H0, and 1 minus dy would be 0. So I don't see that other term. And when dy is equal to 0, I don't see this first term, and I do see this second term. So this is just a way of writing this case-by-case formula into a single value that just flips between the two based on whether dy is 0 or 1. Okay, so now I'm just going to kind of rearrange terms. So I'm going to have a probability of H1 term given y, and then I'm going to have a dy times probability of H0 minus probability of H1, both given y. Okay, and so this is the term I need to focus on. So if this term, so if probability of H0 is less than probability of H1 given y, then this term is contributing negatively to the overall sum and to the probability of error. So I should keep it in those cases by setting dy equals to 1, right? So I want to make the probability of error small. So if this term is negative, that's good. It makes it smaller. So I should keep it. Those are the places I should set dy to 1. If the probability of h0 given y is larger than the probability of h1 given y, then this term is contributing positively to the sum, and I should drop it. And the way I can do that is by setting dy equal to 0 in those places. And you can notice this is exactly what the map rule is doing, and ties don't matter. Okay, so ties don't matter, we're just arbitrarily giving them to 1. Okay, so that's actually the whole argument for why map is optimal. If you open the probability of error in a certain way, and you look at the only thing that you can actually control, dy, then you realize that the only terms you should keep are these negative terms, and that immediately leads you to the map rule. Okay, so why not always use the map rule? So it turns out in practice we don't always use the map rule. So one very good reason is that we may not know the probabilities of the hypotheses. And in those cases, we can still use the ML rule because there we only need to know the conditional probabilities. And this makes a lot of intuitive sense because think about this aircraft example. It's very hard to put a probability of an aircraft appearing by surprise on a certain day. Like, should I put that to 1 over 100, 1 over 1,000, 1/2? I don't know. So that's not something that really makes sense, and then I can collect a lot of data on the fly to set. So maybe that's not the right way to think about it. So you need the ML rule or some other variants that we'll talk about soon. Okay, and it might also be that the costs of false alarm and misdetection are not the same. Okay, so here, when we calculate the probability of error, we're assuming that both ways of making error are equivalent. But let's say that you're trying to decide if a tumor is malignant or benign. If you decide a malignant tumor is benign, that's clearly worse than deciding a benign tumor is malignant, right? Because maybe with one way you just have some extra treatment in general, but in the other way you let cancer go unchecked, right? So you actually want to perhaps put different costs on one kind of error versus the other kind of error.